My name is José Matias. I'm a postdoc at the Norwegian University of Science and Technology. I'm here today to present the work entitled Health Aware Advanced Control Applied to a Gas Lift Oil Well Network. The work was developed together with the bachelor student Joachim Ågotnes and Professor Johannes Jäschke. Well, the outline of the presentation is first, we'll talk a little bit about the motivations of this work. Then we give a brief description of how an economic model predictive controller works. And then we show how we set up our health aware control based on the EMPC framework. And next, we describe the case study, show how we formulated our controller, and then present the results. I will end this talk with some concluding remarks then. Our focus on this work here is the Norwegian oil and gas industry. How is the situation right now? The large Norwegian oil fields are getting older and older, and a large proportion of the original oil reserves has already been extracted. Clearly, that situation requires more efficient process operation to have the same level of profitability. However, older fields also tend to produce more sand. And sand can be very problematic to the equipment because it increases the equipment degradation, and in subsea processes, unanticipated breakdowns can lead to long production halts and large production losses. For you to have an idea, Norwegian companies spent more than 2 billion euros in maintenance in 2018. So the question that we want to answer with this work is, can we and how can we optimize the production while guaranteeing that our system is not going to break unexpectedly? Well, to even further illustrate the motivation, let me show you this example, like to show the trade-off between production and degradation. Let's say that we have an oil rig and we are extracting oil from a subsea reservoir. For some reason, the operator decides to increase the production, and as a consequence, more oil and gas, as well as other subproducts like sand, come out of the reservoir, which increases the degradation of the subsea equipment, especially of the subsea valves. But at this given production rate, the degradation levels are not so high, so the production doesn't have to be stopped. Next, the operator decides to increase the production even further, which degrades the subsea valves. And then instead of producing more, the well has to be shut down due to the high level of degradation of the valves, and they need to be replaced, which is very bad because repairing subsea equipment is very costly. And then you also lose money because you have to stop the production of the well. One way of avoiding it is to try to predict the remaining useful life of equipment based on the operating conditions. That can be very useful and avoid maintenance stops. However, this strategy is normally outlined offline, and it does not take into account what's currently happening in the wells. So what we propose to do is to use a control strategy that combines conditioning monitoring for estimating the remaining useful life of the equipment with control in order to automatically and in real time act on this trade-off. Okay, but then how the EMPC works. Here is this figure that we use to illustrate that. Let's say that we want to optimize the profit of a given system here. At the current time instant, we estimate the current system state, and as we can see here, we are at a suboptimal point. Then the task of the MPC is to calculate the best input sequence to bring the system from the current state to the optimal profit within the prediction horizon NP. Then we implement the first value of this sequence and then wait until the time instant k+1 so we can get new measurements, and then we recompute the optimal input sequence. Why do we do that? By using this recurrent strategy, we take advantage of feedback and compute the best inputs based on the current state, and of course the current disturbance values, and we do not use a nominal trajectory. And what are the benefits of implementing a controller in our process? There are several reasons why someone should do that, but here I list the ones that I consider the more relevant in this work. The MPC is able to improve the system response to feed variations, improves product quality, and increase process regularity. And most importantly, we can include constraints in its formulation. That means that we can find the best input trajectory that does not violate constraints, like, for example, health constraints, such as crack length in the bearings of a compressor. Okay, good. But what we need for a health-aware controller? Here I show how I can formulate the regular EMPC mathematically. First, you have to have an economic function, phi, such as profit, for example, that you want to maximize in the prediction horizon NP. It depends, of course, on the system states X and also in the system inputs U. Then you need a model that describes your system dynamics, and if necessary, you can add relevant process constraints such as maximum capacity, maximum production capacity. For the health-aware controller, we need to do some minor modifications, namely include a model for our system degradation here, which can be a knowledge-based model, data-based model, or a combination of both. And of course, constraints related to the health state of the components that we are interested in. And how does this implementation looks like? The idea is to implement it in a closed loop. So you have a process that you want to optimize without degrading the critical components. First, then we need to process that data that comes from this process. Then we need to have some diagnostics routine that detect the system health state. Then we have the controller that we discussed previously. Since this work is still ongoing and is part of a larger project, we started by first implementing the controller, which we are discussing right now, and we don't focus really on the diagnostics part. Because why we do that? Because we want to understand how and if the controller with this setting works. Now let's talk about the case study. The process of interest is a subsea oil extraction system. How the system works, you have like a reservoir here, which usually contains a mixture of oil, gas, water, and sand. Then we have a well that connects the reservoir to the top facilities. Usually the fluid is pumped out of the reservoir to the facilities by the reservoir natural pressure. However, in some cases, this pressure is not high enough, and then we have to use artificial lifting methods to extract the fluids. One alternative is to use gas lift, where you inject gas in the bottom of the well through the annulus here. The annulus is a void between the production pipe and the external well wall. The fluid mixture density decreases when we add the gas, and then as a consequence, the hydrostatic pressure loss in the well also decreases. Then we can produce more with the same pressure differential between the reservoir and the top facilities. Therefore, the well production becomes a function of the amount of gas that you inject in the system. If you inject more, you will produce more until a given limit, where the pressure loss due to friction starts to govern the pressure, and injecting more gas decreases the production instead. One problem in oil wells, not specifically with gas-lifted wells, but in general, is the degradation of the production valve, or also, as we call it, the choke valves. Since this valve is used for shutting down the well and regulating its production, it is important that this valve does not degrade. However, when the well is producing sand, this valve can degrade very fast, in extreme cases from 3 to 4 months. Here I show some pictures of degraded choke valves. So in our case study, instead of having only one well, we have 3 wells in parallel, 3 gas-lifted wells in parallel. And also we have a maintenance stop schedule in 500 days. And the question is, how do we choose the gas lift flow rates in order to maximize the production without degrading our choke valves? To make the problem more interesting, we assume that the wells are placed in different positions of the reservoir. So each well has a different reservoir pressure and sand outlet flow rates. For implementing the controller, we obtain a phenomenological model of the degradation for describing it in time, and a model for describing the system with mass balances, simplified reservoir models, valve equations, and so on. And we also define some operational constraints and also health constraints. We want to predict the system behavior 100 days ahead, but again, to improve the performance with the system feedback, we only implement a new input every day, and then when we got new measurements, we recompute the inputs for the next 100 days. You can see here that we add slack variables to the problem in order to guarantee that the controller will remain feasible. Why the slack variable is important? Here I show a toy example of how the controller works. Let's say we are at the current instant labeled T0. We have the past information and we want to predict the system degradation in the two next sampling times. Since our prediction, in our prediction, the system will not violate the maximum threshold. So we can produce as much as possible during the first time period, but we cannot keep the inputs at the maximum level in the second sampling time, because that would violate the health constraint. So we decrease the value of the second input of the sequence in order not to reach that threshold. Then what we do, we implement only the first input value. And then when the new measurement comes, we see that we are so close to the threshold that we have to decrease the inputs to the minimum value. However, even in this case, the controller prediction will not be able to stay below the threshold, and the control algorithm will fail. If we add a slack variable in the controller calculation, we allow the controller to not satisfy the constraint, but with a penalization in the objective function. Since we only implement the first input in the sequence, the safety constraint in the actual plant won't be violated. And the controller can say to the operators that something is going to break soon if no maintenance is performed. Now, let's look at the main results. We show three plots here. The one on top shows the value of the gas lift used in each one of the wells during the 500 days period. The second plot shows the value of the erosion in the production with time, as a function of time. The maximum allowable threshold is 2 millimeters. The plot on the bottom shows the total production of the well network. We see that in the beginning, since the equipment is brand new, we can increase the production to the maximum value freely, like this. After reaching the maximum gas lift capacity, we still produce at a maximum for approximately 250 days. After that, the controller notices that if it continues producing at this pace, well 2 is going to break before the maintenance stop. So it starts to decrease the production to guarantee that the well will remain operational until then. Around 430 days, the same happens to well 3. We see that the total production decreases, but none of the valves break before the maintenance stop in day 500, which was our goal to begin with. To end the talk, I want to show you some concluding remarks. In this work, we proposed an economic model predictive control approach that incorporates the degradation models. It presents a good performance in a synthetic case study, but I should point out that this approach depends on a good method for detecting the system health state, and of course, it needs to be tested in a more realistic case study. We are currently working on both things. We have built an accelerated live test rig with a very similar system as the one that I presented now in this case study. We are currently working on implementing the controller in the rig. For that reason, we are also testing different state health detection methods. Among them, PCR, PLR, support vector machine, tree-based models, and also Bayesian inference. Well, that was all that I want to show you today. Thank you very much for the attention, and I will be glad to take any questions. Thank you.